Okay, welcome to logs, and I've already started off with a line here. Welcome to logs, and we're going to start talking about the log basics, and we're going to talk about their properties and give you a good basis. This will be a longer video because I want to go through the basics with you. We're going to use logarithms to solve exponential functions and equations. We're going to talk about the definition of a logarithmic function, the equivalence of exponential and logarithmic expressions, and the inverse relationship between y equals log of x and y equals 10 to the x. We're also going to do one with natural log of x and y equals e to the x. So we're going to do natural logarithms too. Alright, what is a logarithm? Well, a logarithm is an exponent. It's also an inverse function of an exponential function, but it really is an exponent. So if you think of a logarithm as an exponent, then this will help you a lot, all right? So if x is a positive number, the log of x is the exponent. It really is the exponent of base 10 that gives an x. So your calculator is base 10. What do I mean by that? Well, when we count 1, 2, 3, 4. We go all the way up to 10. Then when we hit 10, then we say 10 plus 1, which is 11 and 12. So we count base 10. Everything is on bases. Base 10. So your calculator is base 10. So let's look at your calculator. And if you look at your calculator right here, over here on the left, you'll notice, see where it says log here in the blue and then base 10. When they do the calculator, they actually put them together, because you'll have to hit the control button when you use log, and then base 10 here is like 10 to whatever, and you'll notice here is natural log is above the base e to the x button. It's programmed that way because they are inverses of each other and you will be using them a lot. Alright, so let's go back to our presentation here. So in other words, if y equals log of x, then 10 to the y is x. So this is what I always tell students. If log is exponent, I'm going to say the word exponent when I see log. Equals is, so exponent is y. Now if you don't see a base here, it's assumed that it's base 10. If it's anything other, they'll have to put it there. It's kind of like a square root in that way. So I'm saying my base is 10, my exponent is y, equals x. So 10 to the y equals x, and that's where that comes from. We're going to practice what is a logarithm and to find out more what's going on. And hopefully you'll start seeing a pattern here. So if I do a log of 100, and we're not going to use a calculator, but we're going to rewrite these using exponents instead of logs. So these are all log statements. So all of these don't have anything by the log. If they don't, it's all understood that they're base 10. So you can write that down if you want, but they're all understood to be base 10. So when I write all these, this is saying the log of 100 is 2. So when I rewrite that, the base is 10, my exponent is 2, has to equal 100. So when you say the log of 100, you're basically looking at those two zeros, because I can write 10 as 10 squared. That's why it's 2. Here I say the base is 10, log of 0.01 equals negative 2, exponent is negative 2, so my base is 10 to the negative 2 equals 0.01. Base 10, my exponent is 3, so 10 to the third equals 1,000. Now I look over here, I say, okay, this one is log of 30 is 1.477. I have base 10, exponent is this, equals 30. Here, base 10 to the negative 3, because my exponent is negative 3, is 0.001. And here, log of 10 is 1. This is something you should know. And if you look at it, all these logs, how many zeros there are, this one's going backwards, but that's what your base is, your exponent is, so I say 10 to the first equals 10. Okay, so we just rewrote those from logs to exponents. Now let's practice some more. Let's take the exponents and write them using logs to practice. So these are all base 10, so I don't really have to show it. So I can say the log, if my exponent is 5, that's what it equals. So I say the log of 100,000 equals 5. And notice it has 5 zeros. Here, the log of 6.3096 equals 0.8. Here, the log of 0.0001 equals -4. And the log of 342 equals 2.53. That's kind of interesting. If you were to look at this, see how slow that log function goes? If my x was 100,000, my y is 5. These take forever to grow. And you'll notice when we start looking at the graph, logs grow very slowly because exponential functions grow very, very quickly, and they're inverses of each other. All right, let's practice some more. Now, thinking in terms of exponents, it's often a good way to answer a logarithm problem. Evaluate the following without a calculator. So we're going to do these without a calculator. So if I do log of 1, which is something I told you should probably memorize, there's no zeros there. Or if you'd say in your head, so the answer is log of 1 is 0. If you're not for sure how I got that, you know there's a base there. 10 to something had to equal 1. Well, the only thing it could be was 10 to the 0 power. Log of 10 is something else you should memorize. There's 1 0. I could rewrite this as, because it has a base of 10, 10 to something has to equal 10, which is 1. So these two that I've starred is things you should know. Now, as you look at this, I had no zeros, my answer was 0. I had 1 0, the answer is 1. What do you think of a log of a million is going to be? Well, there's 1, 2, 3, 4, 5, 6 zeros. And if you think about it, 10 to the 6 is a million. So what if I had right here log of 10,000? What would that be? Well, count the zeros. 1, 2, 3, 4, so it's going to be 4. Or 10 to the 4th is going to be 10,000. Now, when you go backwards, this is really a base 10, but you're going backwards, so it's basically negative. So the answer to this is I went back 3 places, so it's going to be -3. Or think of it this way, 10 to something had to equal 0.001. And since that was 1 over tenths, hundredths, thousandths, then it's going to be a -3 because you went the other way. This one right here, this one I'm like 1 over radical 10, I've got to write that a different way. Well, isn't 10 on the bottom really 10 to the half if you did flower power? And then if I take it upstairs, so really what this is log of 10 to the -1/2. And if I do log of 10 to the -1/2, log undoes the space 10. The answer is just -1/2. Now this one is a trick question, log of -100. Notice none of these numbers here were negative. None of them. Some of your answers were your exponents could be negative, but this you couldn't have a negative answer. This is undefined. There is no way you can take the log of a negative number. It's undefined. Why? Because it cannot be written as a power of 10. Ten to any power is always positive, so you can never have a negative answer. Okay. All right, let's look at some of these. The operation of taking a logarithm undoes the exponential function. This means that the logarithm and the exponential functions are inverse functions. So if you look at this here, if I have log base 10 to the n, you could rewrite it and say, oh, 10 to the n equals 10 to the n. You're like, okay. But what this does is if the log and the log 10 are next to each other, it's n equals n. This way works too. If you have a base 10 raised to a log, as long as a 10 and the log are next to each other, you cross it off, say thanks for playing, equals n. I always say thanks for playing. Okay, so now let's try some more. Okay, example 4. So I want to evaluate these without a calculator. The log of base 10 of log of 10 to the 8.5, say, okay, thanks for playing, my answer is 8.5. 10 to the log, they're right next to each other, thanks for playing, is 2.7. 10 to the log of x plus 3 is x plus 3. So I hope you get the idea that the log undoes each other there. Now we're going to evaluate these without a calculator. So a lot of these you're going to have to write where log and 10 are next to each other, so you're going to have to rewrite this. So I'm going to rewrite this as log of 10 to the half. When I do, thanks for playing, the answer is a half. This one is 10 to the log. They're already next to each other, so I can say, oh, the answer is 100. The other way to do this is say, okay, I know log of 100 is 2. 10 squared is 100. So either way, these would work, but they both give you the answer. Here, right here, they're not really next to each other, so you have to rewrite it. So that's the same as saying log of 10 to the negative half. Thanks for playing, negative a half. Here I've got 10 to the log of 1 is 1. So I used logs and I undid it. Let's practice some more here. I have ln now, natural log. Well, now ln and e are the same as log and base 10. So I have them next to each other, so I have to write it as this, ln e to the half. When they're next to each other, I can say, thanks for playing, the answer is a half. E to the ln of 2, thanks for playing, it's 2. This one I have to rewrite. This is just like the one we did. E to the negative a half. Thanks for playing. The answer is negative a half. And then ln e to the 2x. Thanks for playing. The answer is 2x. So there's that practiced. Now I'm going to do a couple more here just so you'll have practice. So what if I had something like this? Log of 10 to the a times, that's an a, 10 to the b times 10 to the c. How would I do that? Well, if you look at all these, they all have the same base. So if I'm multiplying, what am I going to do with my exponents? I'm going to add them. So I really have log base 10 to the a plus b plus c. Now, is log next to 10? You betcha. The answer is just a plus b plus c. Another one, what if I had 0.01 raised to the log of 2? So you say to yourself, okay, if this was base 10, I could try to get them next to each other and say thanks for playing. So I'm going to rewrite 0.01 as 10 to the negative 2, and I have log 2, because that's what 0.01 is. And I look and say, oh, the 10 and the log are almost together. What rules can I use? Well, I can bring this up here and write this like this. 10 to the log, using the log rule of exponents, 2 to the negative 2. Now I can say thanks for playing. My answer is 2 to the negative 2, or 1/4. Let's practice some more. Now I have the log of 10. Well, do the inside first. The log of 10, you should know now, is 1. And the log of 1 is going to be 0. 1,000 to the log 4. Make this as a base 10, so it's 10 cubed to the log 4. They're still not next to each other, so I'm using exponent rules, bringing that up top. So I have 10 to the log of 4 cubed. Thanks for playing. The answer is 4 cubed, or 64. This one I like up here. It's kind of cool because you can do it a lot of ways. So I look at this, say, oh, log of 100. Look at the inside. That's 2. So this is radical 2 minus, this is the log of the square root of 100, which is 10. So we know the log of 10 is 1, so my answer is radical 2 minus 1. Here I have e to the ln next to each other. Thanks for playing. 2x plus 9. Let me add a couple extra here. What if I had this one right here? ln 1 over e plus ln ab. And this is actually, excuse me, not a plus b, but ab. This actually is going to use some of the log rules that we're going to talk about in a minute, but it's a cool one to do. So I want to evaluate this, so I'm going to write this as, this is like e to the first down here, so if I bring it up, it's going to be ln e to the negative 1 plus ln a, since it's multiplied, plus ln b. So I can say thanks for playing, -1 plus ln A plus ln B. Now we're going to talk more about those rules that allow you to pull that apart. And the last one I'm going to add here is, what if I had something like this? 2 ln e to the A plus 3 ln b to the e. Well, I can't really cancel these that well, but you can if they're next to each other. And if it makes you uncomfortable, you can bring this up here. So I look at it and say, well, I have a 2 up front. So if I brought this up, I'd raise that there. So it could be like this, ln e to the 2a plus here, I've got 3 up here to bring it here. But I'm thinking, well, that's not really going to help me any if I bring it up, because still ln b I can't cancel. This will cancel and I'll say 2a. This one I can bring the e down here and say it's 3e ln b, because nothing will cancel on that one. So they try to trick you with things like that. So be careful when you use the rules. Now I'm going to do this slide because I kind of put these out of order a little bit. So I'm going to do this slide first and then we'll go back. I want to do the properties, and we've used a few of them. So we've already realized that log of 1 is 0 and log of 10 is 1. We've been practicing that. And then there's 3 distinct relationships, okay? And then we've got it the other way around where you can say log 10 to the x. I can say thanks for playing. Same thing here. So those things we've been using. But there's really 3 log rules you can use. There's 1, there's 2, and there's 3. The first one is if I'm multiplying on the inside, because remember, think exponents. If you were just talking about exponents, you know that if you have the same base and you multiply, you really are adding your exponents. And if you have 2 bases that are the same and you're dividing them, you're really subtracting your exponents. So you need to think exponents. The other thing you need to know is in the parentheses you can only have multiplication or you can only have division to use those rules. Only. You cannot have adding or subtracting inside. And the third rule is if I take the log of something, I can take the exponent, bring it down front, and it would be t times log b, which we write it this way, t log b. So those are your 3 exponents. Exponential rules, excuse me. So we're going to go back, if I can get that out of the way there, and we're going to do this using the log rules. So now if I have log a times b, I notice there's multiplication here. I can actually pull this apart with addition. Have log a plus log b. And when I have addition, they said, well, x is log a and y is log b. So this is really, I can write it as x plus y. Now this one here is trying to trick you because I have log a divided by log b. And it's not inside the parentheses like I've showed you, it's on the outside. So all I can say was I know log a is x divided by y. I'm not really doing anything with the log rules, I'm just substituting. This one I have log radical b, which I can write as log b to the half. And then I know I can bring the half down front, so it's really a half log b. And since log b is y, it's a half of a y. And the last one on this page is really kind of cool because I have a multiplication on the inside here, so I'm going to pull this apart by addition. So I can say log a cubed plus log radical b, and I'm going really slow. This I can bring the 3 down, so I can say 3 log a plus, this is actually b to the half, isn't it? So I can say plus a half log b. And then just substitute the a and the b, so I end up with x and y. I have 3x plus a half of y. You can't see that, but up here they still want you to use x and y on this page, so that would be my answer. So basically we're just playing around with the rules to make sure that you understand them. We've already done this slide. Now we're actually going to talk about solving equations, and this is what we spent a lot of time in this course. And these are the rules I kind of follow by, and we really do use natural logs more than anything. But you are, first of all, isolate the exponential on one side of the equation. Okay, so you want to isolate your exponential part. I tell the kids do normal math first. All right? Then you're going to take the log of both sides. Only at this time do you start using your 3 rules. You don't even use the rules until here. Then you solve for the variable. So let's kind of go back what we used to do. You remember when I taught you, or anyone taught you in middle school, and they taught you that 3x plus 4 equals 10. So you basically are going to be solving equations like this, but you're going to be doing inverses. So if I said to solve this, you have a positive 4, you'd subtract 4 from both sides because they're opposites, inverse. So I have 3x equals 6. And then the 3 and the x are hooked by multiplication, so I'm going to divide by 3 because it undoes it, so x equals 2. So you're going to be doing the same thing, your normal math part, but then you're just going to use the logarithm on both sides to actually solve them. The other thing you're going to end up being are the king and queens of parentheses. Not so much on these new calculators because you do have a fraction button. So here's my parentheses. So let's put a little crown on them because you're going to be the king and queen of parentheses because you got to make sure that you put it in correctly, or even though your work will be correct, you will get the wrong answer. And the other thing you got to remember is when I hit the calculator button here for log, and we don't use log a lot, so if I hit log and put it here in my calculator, so let me go home and let me do a new document. And I'm going to add a calculator. If I wanted to do it, I would actually want to put a log button in. These new calculators, you have to, down here, if there's no other log there, you have to put a 10 to use it. Make sure that you do that. You have to put a base 10 in there. So let's go back to our notes. Let's solve an equation. So the first thing is normal math. So I'm going to divide both sides by 100. Okay, when I divide both sides by 100, that kind of gets rid of a couple zeros. So I have 2 to the t equals 3,370,000. It's a comma, guys. Okay, now notice I did the normal math first, now I isolated my exponential function. Only then do I log both sides. So when I log it, right here on this step, the 3 rules kick in. There's 3 log rules. Okay, so when they kick in, I can now bring the t down front, so I have t log 2 equals log of 3370000. Okay? Now, the t is hooked to the log 2 by multiplication, and this is really a number. So I can divide both sides by log 2, so I end up with t equals log of 3371234 all over log of 2. And you just put it in your calculator the same way exactly is. Please use your fraction button. So you're going to use your fraction button, which is right over here. Okay, and then when you put it in there, oops, I just made this messier than it is. Let's delete that. So like if I wanted to do that in my calculator, I'd actually do the fraction button first, and then I would do the log button. So I do log right here, base 10, because that's what it is, of right here, 3370000. Okay, then down here I have to divide it by log of 2, so I do the same thing, and they don't tell you the base, so it's understood that it's 10. Whoops, down here, understood it's 10 of 2, and then I hit enter. And I have the CAS version, so I have to have my number be to a decimal. Yours won't do that. So it comes out to be 21.6843. Okay? Alright, let's try another one. When we also solve here for, even if it has natural logs in it, you still are going to do your normal math first. You're going to isolate your exponential function, and then you're going to exponent both sides by the power of 10. So if you see a log or an ln in the equation, you can't log a log. So you're going to undo it by using the power of 10 or base e and then solve for the variable. So this is still the opposite. You're still undoing your equation, but you are using the power of 10 or base e. So let me show you one so you know what I'm talking about. Here's an equation. I have log already in it. You cannot log a log. So the first thing is I'm going to do normal math and get rid of that 3, put it on this side. So I have log of 2x plus 1 equals negative 3. Now, again, I can't log a log. So what I'm going to do is base 10 this. So I'm going to actually turn this into exponents. So I 10 to this equals 10 to that. I've made it kind of big so you can see. When you undo it like this, I say thanks for playing. I really have 2x plus 1 equals 10 to the negative 3. 2x, I'm going to subtract the 1, equals 10 to the negative 3 minus 1. And then I'm going to divide by 2. So x is going to be 10 to the negative 3 minus 1 all over 2. And when I put that in my calculator, I get negative 0.4995. Part of this is you need to practice putting it in your calculator, because I see people do perfect work and their answer will come out wrong because they put it in their calculator incorrectly. All right? Oh, skull and crossbones. This is my be careful page, and I'm almost afraid to put this down, but I have to show this to you. If you have a log and you have a plus inside or even a minus, okay, it's not the same as pulling it apart. You have to have multiplication and division. So here's multiplication and division. If I have log AB, it's not the same as saying log A times log B. This is the same thing as saying log A plus log B, because it's multiplication. If it's division inside, it's not dividing on the outside. It's saying log A minus log B. And finally, log of 1 over A is not the same as 1 over the log of A. If I were really going to do that, that'd be log of A to the negative 1, and then bring it down front. That's negative log A. That is not this. So please be careful that you know the rules, and make sure you check it on the calculator. Okay, now where e used to be as a base for exponential functions, computations are easier with the use of another logarithmic function called log base e. The log base e is used so frequently that it has its own notation, ln x, or the natural log of x. Ln x equals y means e to the y equals x. So here, if you see ln, it's understood that it's base e. You can rewrite it. E exponent is y. You do the same thing, equals x. So it has the same rules, and y is called the natural logarithm of x. I think I skipped a slide. Okay, properties. Properties, same thing. ln 1 is 0, ln e is 1, and ln e to the x is thanks for playing, and I can do this way. We practiced that already. And the 3 log rules go with ln just like they did log. So you have multiplication, you add, division, you subtract, and then if you have it raised to a power, you can bring it down front. Okay, let's practice a couple of examples, and from now on you're going to ln everything. I don't care what your book says, I don't care anything, but from now on you're going to use ln. No log. I don't care what your book says, unless you have a log in your equation. So let's do a couple of these. So I have 5e to the 2x equals 50. First thing I want to do is solve for x, so I'm going to isolate it by dividing both sides by 5. So I have e to the 2x equals 10. Once it's isolated, now I'm going to ln both sides, and as soon as I do this, I can say thanks for playing. 2x equals ln 10, which is a number. And then I divide by 2, so x equals ln 10 divided by 2, which is roughly 1.151. Here, there's nothing to isolate. It's already isolated. So I'm going to ln both sides right off the bat. And when I do that, the log rules kick in. I can say x ln 3 equals ln 100. And then I want to solve for x. So these are hooked by multiplication, so I'm going to divide by ln 3. So I have x equals ln 100 divided by ln 3, which is roughly 4.192. Okay, I'm going to stop right here. I know there's one more slide in this, but we can work on that in class.